Myself K. Sainiklu Verma, ITB, and I'm here to say about present a PPT on advances in polymer integrated optics. Let's get into the topic. First, let me give an introduction about it. The recent surge is demand for photonic components that meet economic criteria as well as technical requirements in the telecom and datacom industries. That has been opened the doors for novel technology that enable unique functions and unconventional high yield manufacturing without sacrificing high performance. Advanced planar polymer technology can fit the bill in every aspect. Today, glass optical fibers are routinely used for high-speed data transfer. Through these fibers provide a convenient means for carrying optical information over long distance. They are inconvenient for complex high-density circularity. In addition, provide the possibility for a much higher degree of ruggedness. Work carried out in a number of laboratories has demonstrated these advantages. Into materials, optical polymers were engenerated in many laboratories worldwide and some are available commercially. Classes of polymers for using integrated optic include acrylates, polymates, and olefins. Companies that develop such polymer include Allied Single Chemical, Photonics, and NTT. Table 1 lists the key properties of proper polymers developed at these companies. Allied Signals has developed a wide variety of photochemical set optical transparent polymers, which are based on combinations of multifunctional acrylate monomers and oligomers together with various additives. These polymers are particularly suitable for partial low loss optical devices because acrylates have relatively low stress optic coefficients and because photochemical processing directly from monomers provides polymer characterized by relatively low internal stress. These combination of materials properties allows the creation of waveguides that exhibit both low scattering losses and low polarizing dependent losses. Upon exposure to actinic radiation, these monomer systems form highly cross-linked networks which exhibit low absorption in the wavelength range extending from 400 to 1600 nanometers. This control of refractive index allows us to fabricate step index or graded index optical wave guide structures with well-defined and reproducible refractive index differences to within 0.001. And in this table we can see that key properties of optical polymers developed worldwide. These are the key properties that developed worldwide. Have a look once. This is the wavelength. And the next heading is optical loss. In this, the results of spectrometry studies performed in all set of acrylites. Notable features in this figure are the region of transparency around the datacom computing wavelength of 840 nanometers, the CH vibrational overtone which are most pronounced beyond 1, and the windows of transparency near 1.3 and 1.55 mm. The wavelength of interest for telecom. Optical absorption in polymeric materials is determined both by the engineers of molecular or polymeric electronic excited states and by the location of fundamental and overtone vibrational excitations of covalently bonded nuclei, such as carbon and hydrogen. The location of these vibrational states is determined largely by the spring constant of the bond and the reduces the mass of two nuclei. Since the vibration energy is inversely related to the refused mass, bonds with low reduced masses have highly low vibrational frequencies. And here we can see the optical loss wavelengths. In this, there are CH bonds, CD bonds, CF bonds, and CCI bonds. This is the wavelength of optical loss. Coming to the next topic, thermal stability. In this, a key characteristic of partial applications is thermal stability of optical properties, since organic materials may be subjected to upon thermal aging. Typically, Such egging results for the formation of partially conjugated molecular groups characterized by broad ultraviolet absorption bands which take off in intensely through the visible. These alloying is strongly influenced by the chemical structures of the original polymer. All through the allied signal polymer systems devised here are acrylic. The chemical characteristics of various backbone segments can vary substantially. For the example, simple aliphatic to aromatic and the ether to ester to urethane. This is the thermal stability temperature. The next topic is humidity resistance. In this, non-elongated polymer was subjected to humidity cycling tests. A sample was prepared on a flat glass substrate. Multiminode 90 in plane bends were produced. The guides were 100 m in cross section and 10.9 centimeters long. The test devices were pigtailed by 100 m crore fiber but were not packaged or protected in any manner. A thin cladding was printed around the core layer to give a short path for the diffusing of water. The sample was cycled between rigorous dry and humid conditions for over 600 hours. Next one, temperature dependence of refractive index. First point, a key differences between polymeric materials and more non-conventional optical materials such as glass is that their refractive index varies more rapidly with temperature. And this large difference is in about 25 times larger in most polymer than in glass. Can be leveraged to produce the efficient thermopatically active optical components such as switchers and tunnel fibers. Next one, refractive index dispersion. Many optical systems rely on having no wavelength depend optical effects that then those geometrical design into the system. Therefore, material depression is generally to be avoided. Topic, polarization dependent loss. First point, another important property affecting polarization transparency of an optical component is PDL. PDL means polarization dependent loss. Next one, measurements performed on single mode waveguides at 150 nanometers, 50 nanometers reveal that the PDL is waveguides can be reduced to below 0.01 dB per centimeters, and the value at interface can be below 0.01 dB per interface. Next, B refrigerants. A key material property impacting polarization transparency is the B refrigerants and its depression. A very sensitive technique of evaluating the B refrigerants consists of measuring the polarization splitting in the reflection spectrum of a bar grating made in the material. Next one, waveguide fabrication. There are three types of fabrications. One is contact printed lithography, laser direct writing, molding. And applications. There are two types of applications. One is telecom and datacom. These are the applications. Let me conclude the topic by conclusion. We have reviewed the key properties of polymeric system developed worldwide for the telecom and datacom industries, and have given a detailed description of allied signals cross-linked allied photopolymer waveguide technology. These materials are characterized by low optical loss, thermal stability, humidity resistance, low refractive index, dispersion, low PDL, low flexibility, mechanical roughness, high photolithographic contrast, capability of precise tailoring of the refractive index, and the ability to be cast in wide range of thickness. The combination of conventional lithography, manufacture, and a brand range of advanced specially polymeric indicated the potential of this technology to be solution to the problem of coefficient production of high performance integrated optical security. These are the references of the given topic. So thank you for everyone giving this opportunity. Thank you.